Hey everyone! In this video we're going to talk about the graphs of the sine and cosine functions. So the graphs of these functions look like what you have here on the screen. We have these wave shapes, and so they just repeat. So it's this waveform over and over again, and when that happens we call these periodic functions because you get the same output values over and over again from the function. It's repeating at a certain time frame or interval. We call that a period. So a periodic function is just a function where you have this repetition of your outputs. So f of x, or the output, is equal to f of x plus n times p. And it's just an integer, and then p is going to be our period, our smallest possible value for when this function would give you the same output. So it repeats. For example, just think of a week. So a week, every 7 days, you're on the same weekday. So if it's Monday, 7 days later, it's Monday again. So you're repeating every 7 days. So here's a graph of our sine function. And the input for the sine and cosine functions is always just going to be all real numbers. And the range will change in the near future when the waves of the graph get higher and lower. But right now, in general, for sine and cosine, the range is going to be from -1 to 1. And that's because the highest up that this will go is 1, and then the lowest is -1. That comes from plugging in our different angle values or arc lengths into our sine function. So recall that sine is equal to the y coordinate on your unit circle for x comma y points. And so if you plug in angle 0, the output for that would be 0 for the y coordinate. If you pick like pi over 2 on your unit circle, just picture that real quick, you'd be up here at the coordinate 0, 1, and so the y value is 1, so that would be the output there. So 0, 0, pi over 2 comma 1, and then we have our angles in between that would give us these other coordinates on the curve, and then we would just plot those points, and that's how we actually get this nice sine wave. And so on this picture we actually have 2 periods of this same wave, so notice you are repeating. If we say that we're starting at 0, 0, then we go up and then down and then back to the starting point of 0, like a y value of 0. So that's one period of the graph, and then we could repeat that, and it's the same sine wave just over and over again. And then over here on the left is the other period of the graph. So cosine, notice it looks very, very similar to our sine wave. The difference is where like the wave shape starts. So for cosine of 0 is 1, so we actually start up here at 1. The range is still -1 to 1, the highest is 1, and the lowest we go on this graph is down to -1. But we start up here at 0, 1 because if you recall from plugging in your angles or arc lengths into our cosine function, cosine is the x coordinate on your xy points on your unit circle. So if you think about right over here, angle 0 or arc length 0, this is at the point 1 comma 0. So if you plug in a 0, your output is 1, and so that's how we get that first point on the graph. And then if we just pick like pi over 2, at pi over 2 we're at the coordinate 0 comma 1, and so cosine is 0 there, so we would be right here on the x-axis, and then all the points in between, we can plot those by plugging in the different angle values or arc length values, and then we get this cosine wave. So we have this shape here, and then this is one period, and then it could repeat and have a second period. Over here is a period on the left, and that's our cosine wave. So if you're noticing that it's the same exact shape, however it's just like a shift over from sine to make the cosine wave. So on sine we start at 0, 0, and then on cosine it starts at 0, 1. So that's the one that starts up higher, but it's the same shape, just shifted over actually by pi over 2. So now we'll talk about the amplitude of the graph. So the amplitude is, think of it like the height. So it's half the difference between the max and the min values. So for our wave shape, it's basically through the horizontal, so half the distance is the amplitude, half the distance up or down. So how high up is this? That would be the amplitude. Or you could say how far down is this, how low does this go? That's the amplitude from the horizontal. So you can tell the amplitude just by looking at the function, by looking at the number multiplying sine or cosine. So if you have your value in front of it, this value a tells you your amplitude of your function. And so the amplitude is the absolute value of that number. So let's say that number is like a -4, then the amplitude we would say is +4. And then that does affect the range of your graph, because what it does is it stretches your graph. It does like a vertical stretch when the amplitude grows. And so for example, if we were to graph sine of 2 sine of x, and as opposed to just sine of x, well, look at this graph. It just, everything got a little taller. It actually doubles. So the dashed one here in the background, this is just sine of x. And then if we say what's 2 sine of x, well, think about what happens. All of your output values just get doubled. And so where you had a height of 1 before, you now have a height of 2. So everything doubled. And so the wave looks like it's stretched vertically, if you remember learning about transformations of graphs. So stretched vertically by a factor of 2. Now, the period of our functions. For sine and cosine, the period, unless there's some extra things going on, it will always be 2 pi. So the period for sine and cosine waves is 2 pi. However, a lot of times you're dealing with these functions that have some extra pieces and some stretching or compressing. And so what you have in general is that the period is 2 pi divided by b, where b is any number multiplying x right here on your function. So let's say you just have y equals sine of x, like we've been looking at. Then there's an invisible 1 in front of that. So you would just have your period here would be 2 pi over 1, which I said a moment ago is the period of sine and cosine. It's just 2 pi. So if there's a number there other than 1 in front of x that's multiplying it, then that does affect the period of the graph. And recall what we said, the period is how often, or the time frame basically, for when the function starts repeating the output values. So for sine and cosine, if you think about your sine wave, well, that one doesn't repeat itself until here, and that value would happen at 2 pi. Okay, so it's the sine wave, we're going up to +1, down to -1, and we don't get those same values out again until after we go to 2 pi, and then it starts over. And the same thing happens with the cosine graph. We start up here at 1, and then we come down to -1, and then we would come back up to 1, and that would happen also at 2 pi. So that would be the period unless there's a number multiplying x, which then would either stretch or compress our graph horizontally. So for example, let's say we wanted to look at the graph of this time sine 2x. So this is different than the last example. Last time it was 2 times sine of x, and that basically doubled the height of our graph. This one is sine 2x, so the x values are doubling, and then we're taking sine of them. So what it actually does to the graph is it compresses it horizontally. So because any x number we plug in, we say twice that, and then we take sine of that, it ends up compressing our graph in the horizontal direction. So notice our blue graph, this is the compressed one. It's taking that value in front of x, that b value, and that's the 1 over that. So 1 over b is how we're compressing the graph, by that factor. So notice if you look at your red dashed wave, we already talked about this a moment ago. This wave, one period is 2 pi. You don't get a repeated value until 2 pi. But then if you take a look at your blue wave, well, on the blue one, if you're going from here to here, notice you're up at a height of 1, you come down to 0, you're down at -1, and you're back at 0 here, and you're going to start repeating after this. So that happened, the repeating starts at pi, and so the before the times 2, the x times 2, before this, we didn't have that repetition start until 2 pi. So now that whole repetition started way earlier because we're multiplying x by 2. So that's the horizontal compression on that type of graph. So let's take a look at this one. We're going to graph this one with a little bit more detail. So graph cosine of 2/3 x. So the first thing we're going to do is figure out what is the period of this function. And so remember b, so cosine of bx, this is b. So you say 2 pi over b, and so you replace that into that formula. And then if you simplify this, you're going to get 3 pi. So this function, the period is a little bigger than our normal cosine x function. And it's because we're actually multiplying x by a fraction. So we're cutting the x values down, so we basically need more x values to cover like a longer period of x values to get the whole cosine wave. Okay, so now what you do, once you know the period, is you're going to divide that period into 4 equal parts to get the x values. So you take that period, if cosine starts at 0 and it goes all the way to 3 pi, you're going to say, well, I want to cut this into nice fourths. So cut it in half, and then cut those both in half. And what are those values? And so you can get those values by just doing a little bit of dividing by 2 a few times. So you would say from 0 to 3 pi, cut that in half, so divide by 2. That would give you 3 pi over 2. And then if you cut 0 to 3 pi over 2 in half, so you say, what's this divided by 2? You would get 3 pi over 4. And then over here, you could do that one maybe in your head if you are able to, or you could write that out. You would say, well, how far is this distance? 3 pi over 2 until 3 pi. So you would just figure out that distance, and then you're going to cut that in half. So real quick, we'll just find the common denominator just to show you the work behind this one. So you would get 6 pi over 2. Another way to rewrite 3 pi, and then minus the 3 pi over 2. And so you're finding out that from here to here, and this is just sort of the side work for this step. So you're saying from here to here, that's equal to that distance of 3 pi over 2. And so you would divide that in half. So you want to cut that in half, and then add that to this piece. Okay, so if we cut that in half, that's 3 pi over 4. So then we'll say this middle part plus 3 pi over 4. And so if you have a common denominator, you would say that this is 6 pi over 4 plus 3 pi over 4. And that's how you would get that this location right here is 9 pi over 4. Okay, so that's how you would divide out your periods interval into quarters. You would split it into 4 parts. And so we're going to use those values to obtain what we call key points for the graph. And you'll see on the next screen why those were good values to choose, because when we pick those numbers that we had divided our x-axis into, so from 0 to 3 pi, we cut that into half and then into half again. And so based on those choices, watch what happens. So if we plug them into our function, so it's 2/3 x, and then we'll take cosine of that. So 2/3 of each of those numbers give us these nice angles that we've been familiar with. So 2/3 times 3 pi over 4, it gives us pi over 2, and then we get pi, 3 pi over 2, and we actually get our quadrantal angles. So then we can easily take cosine of those. So cosine of pi over 2 is 0, and we would plot that point. So we would say at input of 3 pi over 4, even though I inputted 3 pi over 4, I ended up getting out 0. Okay, that cosine, the same as cosine of pi over 2, because I multiplied my input by 2/3. And then same thing with 3 pi over 2, we plug that in and we end up getting -1, and then we plot those points. So notice this is one full period of our cosine wave, and if you compare it to the original function of just regular cosine x, not cosine 2/3 x, it's a little bit more stretched. Okay, it's horizontally stretched because we have to go all the way to 3 pi before the wave starts repeating, whereas with just regular cosine of x, that would start repeating at 2 pi. Alright, next let's talk about translations. So we have what is called a horizontal translation. Very similar if you've learned about transformations previously for any of your other functions or graphs of your functions. So our graph is going to shift left or right if you have a value affecting x inside your function where you say plus or minus that number. Okay, so if you have x minus a number, you actually are going to go to the right, and if you have x plus a number, you go to the left. So here's some pictures for you. So if your original graph is just regular f of x, then if you have minus 4, you actually shift that same exact graph 4 units to the right. So all of your points that you had here would just move 4 units to the right. And then if you have x plus 3, that actually takes your graph 3 units left. So all of your points would just mirror, but 3 units to the left. When this happens, when we have a horizontal translation, we call that also a phase shift, if you've ever heard that before. So horizontal translation or phase shift. And then the expression inside of your function, so like cosine of x minus d or sine of x minus d, that part we're calling the argument. There are also vertical translations or vertical shifts. So these would be a shift up or down. So it just depends on if there's a number getting added to your function. So if we have plus or minus a number, this one's pretty straightforward. Plus the value, we go up, minus the value, we go down. So again, if the original graph is this middle blue one, then f of x plus 3 would actually be the same exact function, just shifted 3 units up for all of your points. And then over here, the green one, f of x minus 5, every single point on your graph would just move down 5, because that's a vertical translation. Alright, so now let's break this down into guidelines for graphing any of our sine or cosine functions. And so notice a couple of things before we begin with the guidelines. The number multiplying sine or cosine, that's going to give us our amplitude. This number b, that helped us figure out the period of our function. And then we just talked about the shifting. So x minus d, the d value would give us the horizontal shift left or right. And then the plus c, this would give us our vertical shifting up or down. So method 1 out of 2 for graphing our sine and cosine functions is 5 steps. First, find an interval whose length is 1 period, so similar to what we just did. And you can do this by solving the following inequalities. So your numbers b and then x minus d, so whatever is next to your cosine or sine function, so like b, x minus d, whatever values you have there, you can basically put that in between the original period of sine and cosine, 0 and 2 pi. And if you solve that for x, so that x is in the middle, so you have x here, and then whatever you get on the left and right, that will give you your new period, your new interval. And then you could cut that into 4 pieces like we did in the last example. So divide that by 4, find the middle part, so find the middle, and then cut the middle, the smaller half in half, and then the upper half or larger half in half. Then evaluate the function for each of those values. So you'll have a 1, 2, 3, 4, 5 values from this interval, and you can plug those into your function. And what that will do when you do it this way, these steps, you'll end up finding the highest and lowest points on your graph and the middle points. So you'll get the height of the waves, the high and the low points, and you'll get those key points like that on the waves. And then you plot those points, join them together with drawing a sine curve, and then any more points if necessary, which probably you wouldn't need any additional points if you use this method. The other method is to use the transformations or translations. So you can just graph your regular sine or cosine wave, but also adjusted for an amplitude and period change. So graphing the function where the wave's height might be higher or possibly shorter, and then also the period might be bigger or smaller. So drawing that graph, and then just seeing if there's any numbers that would make the graph shift vertically up or down or horizontally left or right. So that's another option. So let's try this example here. So notice we have a whole lot going on. So we're going to draw 2 periods of this graph, It is a sine wave. Notice that the amplitude right here, this is 2, so the graph is going to look like it goes higher and lower than our normal sine graph. It's vertically stretched by 2. We do have a shift right here, -1, so that's going to go down by 1, and then all of these things happening inside of our argument here is going to affect the period and horizontal compression or stretching of our graph. Okay, so we're going to write out our form. So the only difference is to take the argument and divide out or factor out the number in front of x. So in this case it's a 4, so we would factor out the 4, and then that's why we would end up getting pi over 4 here instead of just pi, because we factored the 4 out of 4x, so we divided that by 4, and we also had to divide the pi by 4, so that's where the pi over 4 came from. So we'll do method number 1. So we'll say step 1, find an interval whose length is 1 period. So what we'll do is we take this argument here and we'll plug it into our format. From the previous slide we said that this is the b times x minus d, and we just put that in between 0 and 2 pi. So we set that up, and then we start to try to solve for x. And so if you divide everything by 4, if you just divide everything by 4 here and here and here, then you end up getting pi plus x plus pi over 4 in the middle, and pi over 2 on the right, and 0 on the left. And then last you would just need to subtract this pi over 4 from all 3 sides of this inequality. So if you subtract pi over 4 from everything, that's how we would end up with this interval. So here would be 1 period with a starting point at negative pi over 4 and an ending point at pi over 4. And so if you then, step 2, divide that into 4 equal parts, you would get these parts. So let me just show you how we got those. So we know, based on our previous work, that we would start drawing 1 period of this graph at negative pi over 4, and then we would stop drawing it at pi over 4. And we want to cut this into fourths, so we would find the middle of that. So to find this middle value, we can kind of just tell by looking halfway between negative pi over 4 and positive pi over 4 is 0. But in case the numbers aren't symmetric like that, what you would do is you would just say like the average of the two. So you'd say pi over 4 plus negative pi over 4. You just take the two values and add them and find their average or middle. So then you would just get 0 over 2, and that's how we got 0. And then we want to cut those both in half. So half of this, and again, this one you can kind of tell by looking, but in case you're not able to with another example or another problem, you would say that from here to here, how far is that? Pi over 4 plus 0, and then you would divide that by 2, and so that would give you pi over 8. And then over on the left, negative pi over 8. So that's how we could do this part and cut this into 4 equal pieces. And then once you find those x values, then what you can do, and you don't really have to do it in steps like this, you're going to just plug them into your function. So you could, once you get those x values, just plug them right into your entire function. But if you don't have a calculator, or if you're just like using the unit circle, it might be easier to go step by step like this. Plug it in and add pi over 4, then times that by 4, and then find the sine value of that, and then multiply that by 2, and so on. So that's, I would say do that if you don't have a calculator, if you have the unit circle in front of you, and you can work with that, because then these numbers are nice once you plug them in, because you're getting these high and low points of your waves. So notice we got, once we plugged into sine, the sine function, we got 0, 1, 0, negative 1, and 0. So the high and low points of the wave. And then we just times those by 2, so our heights got bigger and lower. And then we also have that minus 1, so everything shifted down because of that. Alright, so then we put it all together, and then you just plot those points that you got from your interval, and then so that would be 1 period of this graph. So 1 period goes from here to here, so that would be this 1 period, and then you can kind of draw another period after that to the right, or you could draw half a period to the right and then another half to the left like this, whichever way you want to be able to draw 2 periods of this function. And so that is our example for drawing our sine wave. Alright, so that's it for this one. Thanks for watching.